Hello and welcome, everyone. My name is Lauren Harrington, and it is my privilege to be the host of today's webinar. Joining me today is a very special guest speaker with a lot to say about everyone's favorite exoplanets. However, before we jump right into that, I do have a few quick announcements to make. First, I would like to point out a couple of features here inside Zoom Webinar, which you might not be familiar with from regular Zoom meetings. If you take a look at the bottom of your Zoom window, next to the chat box where we've all been introducing ourselves, there are two extra buttons. One is the CC or Show Captions button, which allows you to enable or disable Zoom's automatic closed captioning. Then there's also a button which is labeled Q&A. If you click on the Q&A button, you will have the option to submit questions for our instructor. You can submit as many questions as you'd like at any point during the broadcast. Today, we'll be doing a bit more of an interactive workshop than a normal lecture, so please feel free to submit your questions at any time. I'll be reading your questions as they come in, and we will take breaks as necessary during the workshop to make sure that you get your answers necessary to follow along. Now, good news. Registration is open for next month's free webinar. If you happen to be infected by the exoplanet bug today and you want to go further with exoplanet photometry, be sure to tune in on September 14th for our follow-up workshop, which will be all about practical exoplanet photometry. You can learn more and find the registration link on our website at aavso.org/webinars. You can also take a picture of that QR code right there. Another exciting thing which you can register for is our 113th AAVSO annual meeting, which will be held at the U.S. Space and Rocket Center this November, 8th through 10th. This is a must-see event. We've gotten very fortunate with how the venue that we have for this meeting. So we will be holding our opening reception in the Saturn V hall, which is what it sounds like. We'll be dining underneath the Saturn V. We have a stellar lineup of keynote lecturers, including Brad Schaefer, who will be presenting on T. Corona Borealis, which is a must-see, Dr. John Blevins, who's a chief engineer for NASA's Space Launch System, and Sukana Chakrabarti, who is from the University of Alabama in Huntsville, has just been added to our keynote speaker lineup. You can learn more about these upcoming presentations and all the other reasons why you should register for our annual meeting at aavso.org/113. Okay. Now I would like to thank our 2024 series sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. Okay. Today's speaker is an astrophysicist at NASA's Goddard Space Flight Center, where he researches exoplanets. His research focuses on the characterization of exoplanetary atmospheres using both the transit method and direct imaging. At NASA, he is heavily involved in several exciting upcoming space-based missions, including the Nancy Grace Roman Space Telescope, as well as the Pandora mission, for which he's coordinating ground-based support. In addition, he is the project scientist and lead for Exoplanet Watch, a citizen science project in which observers around the world coordinate to observe transiting exoplanets, updating their ephemerides and guiding the use of large observatories. Today, he is joining us to teach us all about his work with Exoplanet Watch, as well as some of the useful tools which the project makes available, and in general, how you can help contribute to the study of transiting exoplanets. It's promising to be an extremely fun event. So without further ado, I would like to introduce our honored guest speaker, Dr. Rob Zellem. Welcome, Dr. Zellem.
Thanks, Lauren. Really appreciate that awesome intro. And thanks everyone for having me and everyone for calling in across the world early on a Saturday, early on a Sunday. Really appreciate it. Also happy to see tons of our exoplanet watchers on the line, like Bruno and Fred and Calais and Anthony and Andre and good Lord, Ira. Thanks so much for calling in, everyone. Really appreciate the support. So let me get my slides started here. 1 second. All right. So you should all be seeing the non-presenter mode. And as Lauren said in the intro, I'm Rob Zellem. I'm an astronomer at NASA's Goddard Space Flight Center. And yeah, my main role is the communication scientist for the Nancy Grace Roman Space Telescope. This is NASA's next flagship mission that'll be launching between October of 2026 and May of 2027. But one of the other projects I work on is Exoplanet Watch, which is the citizen science project for all of you here on the line to help us observe transiting exoplanets. And we're funded by NASA's Universal Learning, which is funded through NASA Space Mission Directorate or Science Mission Directorate. So just a quick overview here of Exoplanet Watch. This is our general launch of Exoplanet Watch. Has actually happened about a year and a half ago. Sorry, I forgot to update this one bullet point here. But this is our citizen science project to monitor transiting exoplanets where anyone and everyone can participate. So you can, by doing hands-on research, you're literally doing the same thing that we do as professional astronomers of using ground-based telescopes to observe transiting exoplanets. And anyone and everyone can participate. The only thing you need is a smartphone or a Chromebook. You don't even need your own telescope. Or if you live in, for example, the Pacific Northwest, which always seems like it's cloudy at night, unfortunately, you can also use our robotic telescopes or the AVSO's robotic telescopes, AVSO Nets, which I think is one of the perks of being a full member on AVSO. You can actually use those robotic telescopes to get your own data from these telescopes and then analyze it through our project. So really quickly, just as a quick introduction to exoplanets, what we're here doing is measuring something or using a method called the transit method. So if we're observing a host star, if we're really lucky, that star will have a planet around it. And if we're even luckier, the geometry will be just right, where the planet passes in front of the star and causes the star to appear to dim. And this method is extremely, extremely helpful and crucial because this measures the size of the planet. The bigger the planet, the more light it blocks out from its host star, the smaller the planet, the smaller dip in light. But this method is also extremely crucial because it allows us to study an exoplanet's atmosphere. So as the planet passes in front of the star, not only is the optically thick disk of the planet absorbing the star's light, but also the very thin annulus of atmosphere. And if we observe how the star's light is changed or absorbed by the planet, by the star, if we observe how the star's light is absorbed by the planetary atmosphere, we can actually back out the composition of the planet's atmosphere as well. So this is actually a very crucial method for enabling us to characterize the atmospheres of these exoplanets. And this method has been used very successfully by some telescopes you probably have heard of before. The Hubble Space Telescope has observed transiting planets, I think about 60 of them now, to analyze their atmospheres. James Webb, which was launched just about 2 years ago, I think 2 years ago last week, actually, or started getting data 2 years ago last week. They have been achieving incredible, incredible results. Almost every single observation of a transiting exoplanet is coming out as like a Nature article because of James Webb's increased size and spectral coverage. Next generation missions like the Aerial Space Telescope. This is a European Space Agency mission that will be dedicated to observing hundreds, if not thousands, of transiting exoplanets. But if we want to use any of these space telescopes to observe a transiting exoplanet, we have to know very precisely when that transit will occur. So for example, if there's like a 15-minute uncertainty of when that transit will occur, that's an extra 15 minutes of overhead we need to build into our observing campaign. And while that doesn't seem like that much once in a while, when you start looking at tens or hundreds or thousands of planets, that's time wasted waiting for that transit to event very quickly accumulates. But this is actually where crucially ground-based telescopes operated by folks such as yourselves can be extremely helpful because a lot of the same targets we're observing with Hubble, James Webb Ariel, even near future missions such as NASA's Pandora mission, a small satellite mission that'll be launching the fall to winter of next year, that's precious time that we're wasting on these telescopes. We could be doing other compelling science. So this is where all of you can help. And that's what made us want to launch this project called Exoplanet Watch. So again, this is our citizen science project to routinely observe transiting exoplanets to keep their transit times precise. So by your participation in this project, you will help us enable additional NASA science, not only sort of giving back to the exoplanet community, but also by making or allowing us to use these telescopes a lot more efficiently and there increase the overall science output of these space telescopes. We're a collaborative effort to complement existing surveys. All of our data is immediately public. You can go to our website right now, and our pipeline is releasing data, I think, every other day right now. And you can grab all of our data on our website and analyze it for your own purposes. We routinely have target requests by professional astronomers who are actually about to start an observing campaign in support of the Pandora mission. So those of our awesome exoplanet watchers that are on the line right now, stay tuned on our Slack channel because I'll be making an announcement hopefully about that in the next week or two. And also extremely crucially, and something that we're very passionate about, is that if you give observations that are cited in a paper and they haven't been previously published, you'll be listed as a co-author on any published papers. And that's because if you do the work, you deserve the credit for all of your amazing hard work. And again, we're very nicely funded by NASA's Universal Learning. So a huge help, or really honestly, a huge thank you to them as well. So as a citizen science project, we have both educational and science goals. The science goals I basically went over just a few minutes ago. That's to ensure the efficient use of large telescopes. But we're also in the discovery and confirmation of new exoplanets as well. So Fred Nuger on the line, thanks for calling in, Fred, is ramping up a project right now to help confirm some new exoplanet candidates. And he has routinely a lot of our users, such as Mike Prim, that participate and help get, and Ira Bell as well, and others on the line to help get observations of those planets to help confirm them. And very soon, we're going to be ramping out a stellar variability campaign as well. We really care about stellar variability because all of our measurements of our transits are differential measurements. We're measuring the planet relative to the star. So if the star's brightness changes, that impacts the measured radius and also potentially the composition of that planetary atmosphere. So in other words, we have to really know our star really well in order to understand our planet. And that's where all of you AAVSO variable star observers really help out and become extremely crucial because we need to know the star as we're going after smaller and smaller planets. We're looking for smaller signals because once those stars start varying, they can have huge impacts to the measured transit signal of the planet. So I'll be sharing some stuff with AVSO folks and hopefully doing some observing alerts for all of you soon, those who do variable star research as well. But we also have tons of educational goals in addition to these science goals. So we're going to be teaching and engaging the public about exoplanets and then enabling them to do science. So really, your workflow is extremely similar to how I am as a professional astronomer of collecting data, analyzing that data, and then submitting it for publication as well. And it's also to help inspire the next generation of folks to become professional astronomers. Kalei Tak, who's a teacher at Stanford Online High School, she's made Exoplanet Watch as part of her curriculum. And I believe she's now had some students that are now pursuing astronomy at places like MIT, which is absolutely incredible. And we really appreciate all of her amazing participation and work on there. So here is our overall user experience map. It's a little overwhelming, so don't worry, I'll step you all through this. If you're lucky enough to have your own telescope, you can actually go on our website right now, and we have the Swarthmore Transit Finder plugin just embedded right into our website. And using that tool, you can type in your location and you can hit go, and it'll tell you the exact transits that are visible from your neck of the woods on any given night. And on any given night, there's at least tens of planets that you can observe any single night. So there's a lot of opportunities and options for you to observe. Then once you pick your target, you go out and you go ahead with observing. And I'm sure in the amazing workshop that Dennis Conti runs, he'll probably talk a lot about observing and also image analysis. So I'll skip over that a little bit. But transit observations are pretty straightforward. You slew to your target and you sit on it all night and just do regular photometry. It's really, really simple. If you can do astrophotography, this is so much easier. Even I can do it. So I'm not great at astrophotography at all. If you live in a neck of the woods that might have perpetually cloudy skies, maybe it's had bad luck, or you don't have your own telescope, you can actually request data from us. We've been very, very fortunate that the micro observatory run by Harvard's Center for Astrophysics out in Tucson, Arizona, they've donated over 11 years worth of data to us of transiting exoplanets. So we have hundreds, if not thousands, of data sets that we need your help to analyze and reduce. So you can go on our website, fill out your email address, fill a little captcha to prove you're not a robot, and then you can actually get data delivered to your email inbox in a few minutes. And right now, you can request a new data set roughly every 4 days. Well, hopefully by the end of this year, if not the end of the summer, we'll be shortening that data checkout system to about once a day. And we're starting to replenish that with more micro observatory images. But we also have about 6 telescopes at JPL's Table Mountain Observatory, that's northeast of Los Angeles, where we're getting those telescopes automated. And about 2 of the 5 are fully automated right now, a 0.4 and a 0.6 meter. The other 3 and to 4 I'm getting set up right now, and we'll hopefully get those up and running and put those into the hopper as well. All right. Then once you get your data, either with your own telescope or through us, you can then analyze your data. I believe Dennis will be talking a lot about the Astro Image J analysis package, but you can use whatever data analysis tool you want. You can use your own homegrown system. HOPS is a really popular one that folks who participate in the aerial mission through Exoclock provide. I'll be talking about Exotic today, and Tamal will be putting a link at the end of this talk, and that will be actually part of our user participation part of this talk as well. So I'll get that to you in a minute, or if any of you Exoplanet watchers want to add that link, feel free to do so in the chat. But once you analyze your own data, you then upload it to the AAVSO website, the Exoplanet database. Thank you, Clay. And we are extremely, extremely fortunate, and we really appreciate being able to partner directly with the AAVSO and to have them let us use their database for hosting all of this data. This is a huge help, and we really, really appreciate it. So thanks everyone at the AAVSO for helping us out with this. Then, once you've shared your observations to the AAVSO Exoplanet database, you kind of sit back and relax. You can get published. A lot of the Exoplanet watchers on the line, such as Clay, have actually been co-authors on multiple Exoplanet Watch papers and have provided extremely crucial data. Or you can publish your own results as well. You can go on our website and analyze any of your data, any of our data right now. The only thing we ask in return is that, again, if you're publishing a light curve that hasn't been published before, you offer those amateur astronomers, those exoplanet watchers, to be co-authors in your paper. Again, if they did the work, they deserve the credit. You cite our paper, and then you add an acknowledgement to the end of your paper as well. Pretty low bar for using our data. And thanks, Mike, for throwing that link in there too. So I talked very briefly about Exotic. I'll also be doing a little workshop in a few minutes where I'll demonstrate Exotic and then leave plenty of time for questions and answers at the end. But Exotic is our exoplanet transit interpretation code. This is a real astronomy analysis tool. This is literally actually the same exact code that I and other folks use as professional astronomers. So it does multi-object photometry, it does your calibrations, your flats, your dark, your biases. It picks out the ideal comparison star. It figures out the ideal aperture size, the sky annulus size. It does an air mass correction, and it also does a fully statistical fit to your data as well. So what it produces at the end of the day is things like a light curve. So we're observing here the host star's light. And then as the planet passes in front of the star appears to dim here. So that's getting a little bit dimmer. And then when the planet gets out of the way, the star gets bright again. So this is actual data produced of HAP P32b, a hot Jupiter. It produces other helpful things, just like AIJ does, like the field of view. So there's our target star and our comparison star. And if you run it locally on your own machine, there is also a real-time data analysis tool. So you can actually see your light curve being produced in real time. So if you're at a star party, for example, and you want to observe a really cool transit with your telescope, you can actually observe a transit and then point to your computer monitor as people are walking by and tell them that you're observing a host star that's being transited by a planet that's casting a shadow all the way here on the surface of the Earth, millions of miles away, which is pretty incredible. All this code runs fully in Python, and there's two main ways of running it. One is locally on your own computer, and that's a perfectly fine way. A lot of our amateur astronomers that have very large data files will run it locally on their own machine just because it's a little bit faster and easier for them to run it that way. But we also have it running on the Google Colab cloud. So those who aren't aware, it's basically a way to connect to Google servers using your free Google account to run software through files in your Google Drive. So a majority of our users will be running and have been running Exotic on the Google Colab cloud. They'll request data from us, from our data checkout system. They'll transfer those files from our server to their Google Drive, and then they'll use Exotic on the Colab to run everything in the cloud. So Exotic doesn't run locally on your own computer in this sense. You don't have to worry about installing Python or Python packages, which admittedly can be very confusing, especially for someone like me. So this really makes things a lot simpler and a lot more user-friendly because you can actually run it even on your smartphone. And I've done it before. I've run Exotic through the Colab Cloud all from my smartphone. You don't even need access to a computer, which is really helpful for folks who might not be able to have a nice, MacBook Pro plus Max or whatever they call it these days. And the person that really helped us sort of lay the foundation of putting Exotic on the cloud, on the Google Colab, and this really simplified everything for us was Kalea Talk. So a big shout out to her and her students for leading the charge there and letting us know that this is an option. It really has truly simplified the workflow a ton. And yes, as Anthony mentioned, there's an Exoplanet Watch Slack channel as well, which I'll talk about in a second. We've been really doing a lot of really incredible science through Exoplanet Watch. We formally launched this, I think, about a year and a half ago, and we now have, I think, over 2,600 people sign up for our Slack channel worldwide. We have thousands of data sets, and we've saved a few hours as well of James Webb Space Telescope observing time. And a lot of these folks are on the line today, despite being tired of my terrible bad dad jokes. So thank you everyone for all your amazing support. And really, really appreciate you all helping make this a really successful project. One such a campaign where we all sort of joined forces was to observe this exoplanet called HD 80606b. At the time, this is the longest transit observation ever done from the ground, as far as I'm aware. And this transit duration is about 12 hours long. So it takes about 12 hours for the planet to pass from one part of the star to the other. So it's literally impossible for any single user in the world to observe the full transit and also the necessary out of transit baseline to better analyze your data and remove error sources. So given this, what we did instead is we effectively simulated a large ground-based telescope by leveraging multiple amateur astronomers and also our amazing Las Cumbres Observatory observing time as well. We got some data on their telescope in Texas, I believe. So we were able to effectively simulate a single large ground-based telescope. So we had people in Eastern Asia and Japan start analyzing and observing this target. They then passed it over to folks in Eastern and Central Europe. Looks like some from the Canary Islands jumped in, and they handed it off to folks in the Western United States. And we were able to stitch all the data together to make this one comprehensive light curve. And having this distributed observing campaign was extremely helpful for many different ways. And one of the reasons is that, for example, it enabled us to observe this very long transit event. But also, of course, the clouds, I believe, are sentient creatures. I think they know when we're trying to make observations and have high priority observations because, of course, most of the northern hemisphere of the entire world was clouded over that night. So we actually probably had another 30 observers, for example, in Western Europe and the Eastern United States, that were completely clouded out. So having this worldwide distributed network is extremely important because it almost guarantees that we can get observations of any exoplanet on any given night. So we actually had 24 facilities here in this campaign. The largest telescope we had was a 0.7 meter or 30-inch telescope. The smallest telescopes we had in this campaign were the unistellar EV scopes, and those are about 4.5 inches across. So you don't need large telescopes to observe transiting exoplanets. I saw, for example, a thread a few years ago, someone just used a single DSLR camera to observe a transiting hot Jupiter. So if you think your telescope is too small, it's not. You can actually observe a lot of these targets. Most of them are 10th magnitude or bigger. Their transit signals are typically about 1%, and those are relatively large signals. So, for example, I was at a dark sky party a few months ago, and there was someone operating an amazing, I think it was an 8 or a 10-inch telescope, and they were getting amazing real-time images of the Sombrero Galaxy. And they thought that their telescope was too small to do exoplanet observations. That's definitely not the case. You can do amazing observations with small telescopes, even from locations without perfect skies. So Anthony Norris, for example, is down in Mississippi where there's high humidity and sometimes cloudy nights. And with his telescope, he's able to get amazing observations. Similarly, Mike Prim has a unistellar EV scope out in Austin, Texas. High humidity again, sometimes also clouds. 4.5-inch telescope, and he is able to get routinely every single night incredible high SNR observations. So don't count yourself out. Give it a shot and see how things go because you might be very, very excited and surprised to see what you can do. So I'm going to then take us to the next slide. This is our Exoplanet Watch QR code. If you get out your phone right now, you can scan that QR code, or you can memorize our website. But personally, I can never remember QR codes or URLs. So if you want to, you can just Google NASA Exoplanet Watch, and that'll take you right to our website. It should be the very first thing that jumps right on the very top. Like Anthony said, we have an extremely helpful Slack channel that I'll show off in a second, where if you have any questions, comments, concerns, feedback at all, you can jump right on there and there's going to be guaranteed someone awake on our Slack channel that can help answer your question. And if not, within the next few hours. And it's also on my own personal phone, so I'm usually routinely answering questions even on weekends like today. So you can definitely get help that way as well. So what I'm going to do right now is I'm going to take a pause to drink some water. I'm going to read through the 3 questions we have in the Q&A, and then I'll do a demonstration of our intro version of Exotic on the website. So one quick second. All right, so our first question is from Katie Wilson, who is asking, is there a size limitation on the atmospheric data? Are we able to determine atmospheric composition on smaller planets? And the answer is yes. We can actually observe the atmospheric composition on even Earth-sized objects. So the TRAPPIST-1 system, for example, is 7 Earth-sized planets around a M-dwarf star, so a star 10 to 100 times smaller than our own sun. And they're actually able to look for little bumps and wiggles in those planetary spectra with the Hubble Space Telescope and James Webb. And they're able to determine that there's, for example, likely water in the atmospheres of these planets. So yeah, with your small ground-based telescopes, we find that typically you need about a 1.5 meter telescope. So that sort of class or larger in order to actually do it from the ground, just because it's so much more difficult to do it through our scintillating atmosphere. But yes, you can use these telescopes to characterize the atmospheres of these planets. Patrick Kavanaugh is asking, can you use light curve with Python to help analyze transits of tests? Yes, you can. We actually do it on our website automatically as well too. So if you go to our website and you click on our results page, I'll step through that in a minute. You can actually, I think we use the light curve package ourselves to analyze that test data and fit it, but that is another way you can participate as well. You can download the test data and analyze that yourself too. We have a question from anonymous attendee. A few years ago, I tried to catch a transit, but the random noise was always greater than the millimagnitude level dip of the transit, and I can never definitively capture it. Is there any trick for reducing the noise down low enough the dip isn't washed up by the noise? There's a variety of different things you can do for this. And quite honestly, that will take a very long time to answer. In short, though, what I recommend is trying to go after one of the big two brightest exoplanets. Those are HD 209-458b or HD 189-733b. Those are about 6 magnitude, and they have transit depths about 1%. Then once you start observing those targets and you sort of cut your teeth on them, for lack of a better term, you can gain a lot more experience and knowledge and then use that to help improve your own observations of dimmer, smaller targets. What I would recommend is signing up for that Exoplanets workshop, because you'll get a lot of great pro tips there, but also hop on our Slack channel. We have a whole observing side channel where you can ask questions from other folks that have a ton more experience than I do that can give you lots of helpful tips and tricks. Let's see, the next question is, I want to publish a paper on exoplanets. I'm analyzing data, have uploaded data results to AVSO, and there's some in the Exoplanet archive. How should I start writing and publishing my paper? That is also a great question and something I'm still learning myself. What I would recommend you do, and I'll show this on the website in a second, is you can look at some of our publications that have been written by other people. And that can give you an idea of what sort of work and background knowledge needs to go into these papers, as some of them do require a ton of work. But one amazing place that I definitely recommend you think about submitting your paper to is the Journal of the AAVSO, the JAAVSO. And that's where lots of folks, such as Clay and her students, have actually published quite a few of their own peer-reviewed papers. We're also happy to help you out on our Slack channel as well. All right, 2 more questions before I go to our website and give you a little work through of exotic. Steven's asking, what is the minimum acceptable SNR for a good observation? Honestly, it varies by the targets. Some targets will be extremely bright, like 4th, 5th, 6th magnitude, and you can achieve higher SNR. Some are going to be a lot dimmer, like 10th, 11th, or 12th magnitude. But it also depends upon the transit depth. So for example, if we're observing a brighter star like a 6th mag, that'll decrease our SNR and the scatter of our data. And we can, since we have higher precision, smaller scatter in our data, we can actually observe smaller transit events. In contrast, if we want to observe a 10th, 11th, 12th magnitude star, that's going to be limiting us to probably Jupiter-sized targets, larger transit depths. The bigger the signal, you can see through the scatter. The scatter also depends on your observing exposure times as well. Typically, what we like to do is get a 3 sigma detection on the transit dip or the transit depth of your light curve. That's where if you take the transit depth and divide it by your uncertainty, that number is greater than or equal to 3. And you can actually achieve that the Micro Observatory. It's a 6-inch robotic telescope out in Tucson. It's been doing that for the last 11, 12 years to very high degree of success. And then the Unistellar folks, such as Mike Prim, have been doing it every single night for like the last year or 3, and have been getting incredible SNR, even with a small telescope. So I think the point of this answer really is just give it a shot and see how things go. Post your results on our website. We can offer some tips and tricks as well. Barbara Harris is asking, is ground-based spectroscopy helpful for determining exoplanet atmospheres? And the answer is yes, for sure. But the smallest telescope that I'm aware of that can do transiting exoplanet spectroscopy, where you can actually measure the spectral signature and the atmospheres of these planets, is the 3.5 meter IRTF, which I did, good Lord, it's probably now been about 15 years almost. And that was on Mauna Kea in Hawaii. So you need a very large telescope to actually get spectroscopic information from these targets. But you can get ground-based spectra on smaller telescopes of the host stars themselves. And that data is extremely helpful for helping us to basically quantify and characterize the host star for spottedness or for flaring or even for the properties of the star as well. So while you probably can't actually observe the spectroscopic transit of an exoplanet using a small ground-based telescope, you can get spectral information on the host star. And then from that, you can help directly enable and complement existing exoplanet data. So I'll come back to the Q&A. I'm going to give you a walkthrough of Exotic first. Let me open up Chrome here. And you guys can all do this as well and follow through me in real time. You have two monitors. You can put one up and open up your own web browser. I generally recommend to use Chrome because it just seems to work typically better with Exotic because it is running the Google environment. But I've also been able to run it on like Firefox, and I've also done Safari as well. So the first thing is to search for our project. So Exoplanet Watch should pop right up. So if you Google Exoplanet Watch, you'll get to our main website right here. And we have tons of helpful information. We have a quick overview. We have a get started page, but a lot of really helpful information can be gleaned from our Slack channel. You can actually sign up for free on our Slack. This is a messaging service similar to like an instant messaging service or a Discord or forums, where you can interact with the Exoplanet Watch team and other extremely helpful folks on our Slack channel, like Prim and Anthony Norris and Ira Bell and other tons of folks that have called into this talk. And you can ask us questions, and other awesome folks will give you tons of advice and help. So our Slack channel is in a very crucial way to stay in touch with our project. You can also sign up for our monthly newsletter right here as well. And that's extremely helpful for highlighting like our member of the month and any of our upcoming observer campaigns. Then under here, this is our how to get started. I'll be coming back to this as well, but it gives you a quick overview of how to get quickly started with your Exoplanet Watch. Embedded in here, we also have these really helpful videos of our biweekly meetings. We've been doing these back to basics campaigns, where we've been going back and highlighting introductory videos on like how to get data from us, how to publish your data, how to analyze your data, and they're all on YouTube and linked through the YouTube as well. We have recommendations on how to observe. For example, if you have your own telescope, we have our own observer's manual. We also have Dennis Conti's awesome guide linked here as well. We have how to request an exoplanet observation. So right here, you just fill out your email address. You can also sign up for our monthly newsletter, and then you have to prove you're not a robot. And within a few minutes, you'll get it delivered right to your email inbox. We also have how-tos on how to analyze your data through Exotic, or you can also use anything like Astro Image J, for example. I know that Dennis is an expert in. We'll teach you also how to become an expert as well. Then how to submit your own data. If you do have your own telescope, we'll come back to Exotic in a second, but if you do have your own telescope, we have embedded in our page the Swarthmore Transit Finder down here below, where you just basically from this drop-down list, you select your location on the Earth. So if I wanted to observe, for example, from Mauna Kea, and I wanted to see what transits were available tonight, I just hit submit, and up will come a nice list of transits available for observing. We also have videos on how to point your telescope and what to select for observing that night. We have a link of helpful resources. And also we have here to answer that other question in the FAQ, or the Q&A session here, we also have a list of publications. So these are all the papers that have been published by folks. And a lot of these were actually written by students and citizen scientists. So Heather Hewitt, she's a PhD candidate at the University, Arizona State University, excuse me, ASU in Phoenix. Fred Nuger, he is an undergrad, also on the line. Thanks for calling in, Fred. Just published a paper about WASP 77AB. Lawrence Rowe, she is at Unistellar. Arvind is a student. Heather is I just mentioned Heather, but most of these papers are written by amateur astronomers, citizen scientists, and students. And only I think about 2 or 3 of them actually have been written by professional astronomers, myself and Kyle. So we really do appreciate everyone's help and support with this. So you can check those out to see what sort of the bar is for publishing. Then you can go to also our results page once my computer wakes up. Yeah, maybe my computer's gonna be too slow. Sorry, I have a loaner laptop that is a little slow. But here we've immediately published all of our light curve data. So we actually have over 446 targets and about 69, good Lord, almost 7,000 data reductions. For an idea of what I was hoping for by the end of this year, I was hoping for about, at the end of 2024, about 300 targets and about 2,000 reductions, maybe even 3,000. But we're annihilating that. Awesome work, everyone. But here you can access all of our data and you just click on your target. You'll go to that website about this target. There's a little cute plugin here from Eyes on Exoplanets. Just taking a little long to load on my computer because it's slow. But here's all the Exoplanet Watch observations. Here's the binned light curve, all the data sets combined together. And then we do a search for other external planets. But what's really cool is we list here all the light curves that have been uploaded to the AAVSO. And listed below it is the observer code. So if you want to use this person's data set in your published paper, the only thing you have to do is you can get the data in a variety of formats. Then you can click collaborate and publish, and it'll open up your email client, and you can email the AAVSO, and they'll reach out to that user to see if they're interested in becoming a co-author on your paper as well. All right, so let's now get into exotic, as that's one of the main things we want to highlight today. So exotic is our exoplanet transit interpretation code, and we have 3 different versions. We always recommend that everyone, regardless of how much experience you have with ground-based observing or data analysis, takes our beginner tutorial. We'll be stepping through this in a second. Then standard, this is our version that most of our users will use. Those who get data likely from us, from the micro observatory, use standard. And then really the only difference between standard and advanced is advanced is more so for folks who have their own observatories and make their own observations or get data from a non-Exoplanet Watch telescope, such as potentially the LCO, for example. And really the only difference between standard and advanced is a little bit more buttons and knobs that you can tweak here as opposed to using the standard version. But we always recommend people use the beginner tutorial just so you get a nice overview of exoplanet data analysis. You'll notice right here, I'm already signed into my Google account. You will need a free Google account in order to use this. Again, it's free when it comes with like 5 gigabytes of storage space. So it's in your interest to get it as well. But all of our versions of Exotic run in this notebook format. Again, we're connected to a Google computer in the cloud, and we're running Exotic, that code in the cloud. This is not running on my computer at all, which is great because this large laptop I have is extremely slow. But all of these versions of Exotic have extremely helpful information in them. So I definitely recommend you take your time to read through it because it has lots of helpful tips and tricks on how to analyze your data. But honestly, the data analysis and running through Exotic is as simple as hitting these little play buttons right here. Let's hide the code. Once I hit play, this will just warn me that Google did not write this notebook. That's fine because Exoplanet Watch did, so I'll run it anyways. And the code will now start to run on the computer. We're connecting to that server in Google. And right now what's happening is it's downloading a bunch of software to the Google computer. So you're not installing Python, you're not installing the packages at all on your own local computer. And this is a huge time saver because getting all the packages installed and set up locally on your own computer can be extremely confusing and a pain. So I'm on some only okay Wi-Fi, so this might take a little bit of time. This sometimes pops up, not a big deal. You just hit restart session. This is just a way to install Python packages. We're working on fixing this for future versions of Exotic. So we're going to restart our pipeline and rerun it by hitting the play button. Now we're just waiting for the code to run. Of course, it's not going to happen in real time because I'm probably on the spot. So while this is thinking, I will go and just double check the chat for a second. And folks, if you want target lists, I definitely recommend you hop on our Slack channel because we post the target lists there, and also we email them out in our our newsletters. So we're trying not to email people on a one-on-one basis because we have lots of folks that want to participate, and that would just be overwhelming for us to stay on top of that and email folks out. So please jump onto our Slack channel, and we'll tell you the user lists from there as well. So right now we're installing everything on that Google Colab cloud. It's importing all the necessary software libraries. Check the Q&A. Restart our session. Of course, this is not going to work because I'm doing it real time. This is not a great time to do this, Google. Let's see, someone's asking about Exoplanet Watch ensure long-term sustainability. So we actually are funded for the next few years by Universal Learning, and we'll hopefully be funded again for about another 5 years after that. So that's typically our funding cycle. And yeah, by publishing these light curves and these data sets, we've identified ways of figuring out which planets require ephemeris refinement and need those measurements of timing information. So I'm on, excuse me, the science teams for the Ariel mission and the Pandora mission. So I'm working with those teams to make sure we're observing their targets to help them out. So we're always doing relevant observations. All right, so there we got the code installed. So here we installed a bunch of Python packages on that remote cloud. We've imported those libraries, and Exotic, in this case, the sample has automatically also downloaded the sample data as well. So this is the next step, identifying our target star and comparison stars. This is arguably the hardest part of the entire project. We have a little video right here that enables you to get some tips and tricks in identifying the star's coordinates, but I'm going to skip ahead because I'm going to show it to you live. What this does is this displays your very first image in your data set, and it also shows this extremely helpful FOV plot. So this is really an amazing plugin that we're really grateful that AAVSO has done for us, and tons of folks have actually identified comparison stars automatically in these fields of view. And so we really appreciate the AAVSO Finder charts for this. It really makes things a lot easier. But from now, what you just do is pattern matching. This tells you where your target star is by the little crosshairs. It also identifies, using these numbers, recommended comparison stars that have been identified by the AAVSO. So Chuck C, for example, has been extremely helpful with doing these star fields. So thank you guys for all of your amazing work on the AVSO side of things. I've seen these two images tons of times, so I kind of know where to look. What I usually do is I look for patterns that are sort of big scale with bright stars that make it easy to find. So you see, you have this collection of stars up to this star, and we have this other backwards pattern. And I can actually find it here on our chart. So there's that grouping of stars, the 4 here, and then the 3 bright stars are 1, 2, and 3. So that means that my host star should be here. But what's really helpful is this little plugin has ways you can zoom in, for example, to make it a little bit easier. Oh, apparently I didn't move my mouse enough there. To just do the pattern matching and make it a bit easier to find. You can zoom in and out. You can move your field of view around. You can also draw, like here's my pattern here to match my pattern there. And that means that my host star is likely that dude right there. We've also cheated here and told you exactly what the pixel locations are, 424, 286. That's pretty close to that pixel position. You just hover over it with your mouse, and then you push enter. And then what you have to do is identify your comparison stars. These are bright stars in your field of view that are ideally non-variable stars as well. So let's zoom out. And according to the AVSO Finder chart, this star, this star, this star, this star, and this star are all good comparison stars. So you just hover over your mouse and you just mentally make a note of those pixel positions, 523 and 326, or 333, 365. I'm just gonna cheat and copy and paste those two stars already in that format into our Colab cloud. So what we've now done is we said, all right, Exotic, in this image, here's where our target star is. And then also within our image, we have these comparison stars. The comp stars are important because they enable us to map out systematic errors. So there's a bump and a wiggle that shouldn't be there, that was induced maybe due to a change in seeing, or maybe a very high cirrus cloud went by, or maybe you accidentally bumped into your telescope. You can actually use the comparison star to monitor for those systematic error sources. Because comparison stars should ideally be flat. Its brightness should be constant with time. And therefore, any deviations from that flat line are due to systematic errors when you divide out. And if we've chosen good comp stars, those same systematic errors that are induced in our comparison star light curves will also show up in our target star light curves. So we can divide the target star by the comp star in order to remove those shared systematic error sources from our data set. So that's why we need the user to not only identify the target star, but also comps in the field of view. Now, you might be worried that, hey, doing the pattern matching is a big pain, and I'm really worried that I'll select the wrong star. You don't need to worry about it because Exotic will check your work. It will upload your first frame from your FITS directory or your files to astrometry.net. We'll do a plate solve of your image and we'll check the RA index of your target star that you've identified with the star that you actually want to observe. So it'll double check your work. Also, we're able to do that automatically for the comp stars. So there's an option there to automatically include the AAVSO comp stars as well. So yes, this can be a little bit of pain to do the pattern matching. But if you mess up, it's not the end of the world. You can, your data, your answers are checked. And that's honestly mostly about it. You just need to install the packages. Let me zoom up properly. You need to connect to the Google Colab Cloud and install those packages. You might hit restart session once or twice like I did. You then do pattern matching here. I've just completely screwed up the aspect ratio, but that's okay. Do some pattern matching between your first image and the AVSO Finder chart, and do comp stars and target stars, and you hit go, and you'll run Exotic. And then Exotic will take typically about 5 to 30 minutes to run. If your images are smaller, or if you have less images, it can only take about 4 to 5 minutes. If you have a digital camera that has a giant field of view or large file sizes, it could take 10 to 30 minutes to fully run. But what's really great is Exotic will give you full posteriors of all of your measurements. So it'll give you the measurement value as well as the uncertainties. And you can directly copy and paste those into a published scientific paper because that's what's required for a science paper. But out here, here's our light curve. So this is HAPI 32b as observed by the Micro-Observatory, the 6-inch telescope in Tucson. Here's the host star brightness. The host star gets dim. The planet gets back out of the way. The host star gets brighter again. And there's your light curve. Then you'll upload this file and the text file that Exotic makes directly to the AAVSO Exoplanet database. And we have instructions and tutorials and videos on how to do that. So Exotic fully takes your FITS files, your images, calibrates them, and analyzes them fully into this light curve. It produces a single text file then that you contribute and upload to the AAVSO. So I'm going to now look at the chat and the Q&A. So we have a lot of great questions here on the Q&A. Abbas is asking, for the sample data, is the data related to possible exoplanet investigation or sample for learning? How can I distinguish those from actual exoplanet study and future papers? So the the sample data here is HAPP32B. It's the single data set that we give out to everyone. I would recommend people analyze and reduce to make sure that they know what they're doing and that they can run Exotic successfully. This is also just a really nice data set, to be honest. But for papers and things, what will typically happen is on our Slack channel, we'll give folks alerts of either campaigns. So for example, Kalain or students had a campaign a few nights ago, I think of Cutter 2, if that's the target I'm remembering correctly, where they asked for help on observing this target. And she got observations from people across the entire world. Or Fred, for example, is going to be asking and has asked for help, and so is the Unistellar folks. So we'll have these campaigns where folks can help us analyze these targets and also hopefully then write papers about them. For Gary, he's asking for the targets via Exoplanet Watch. Are they confirmed or candidate exoplanets? So the cool thing is you can observe any target that you want in the entire sky, any transiting exoplanets. Um, we are typically observing confirmed planets, but we're starting to get into the candidate exoplanet game. Right now, you can only upload confirmed planets to the AVSO exoplanet database, but hopefully we'll get some funding awarded that we'll hopefully hear back soon about that will enable really folks like, folks like Bert Pablo to then expand and add candidate planets to the AVSO database. But if you want to help out candidates, we can definitely start doing that as well on our Slack channel. So just get on our Slack to be in the loop. Jay's asking about EVscope or C-stars. I think people have been using C-stars on our channel, and I haven't personally seen the data posted just yet, but I know that people have been. I'm pretty sure. I would go onto our observing channel and ask there just to be safe, because people will know better than I do. Lisa's asking, are targets being separated by region or collectively integrated with global citizen scientists? We're doing both, quite honestly. Some of our planets will be observable only from certain parts of the world, such as North America or maybe Southern Africa, for example. But some of our campaigns will be across the entire world, like we had back in 2021. So they definitely change and vary by the brightness and the duration of the transits. Tom is asking, with atmospheric exoplanet characterization, what color techniques are applied in the light curve analysis? And honestly, it's everything. So from a single photometric channel, you can measure the host star by looking at the limb darkening. You can also look at the mid-transit time just over multiple observations to look for additional exoplanet targets within or exoplanets within that that solar system. But it kind of depends on the science case. It depends on what sort of features you're looking for. So unfortunately, that's a little bit too big of a question that I can't answer just live. So maybe post it on our Slack channel. I can spend a few more minutes to answer the question if you don't mind. Lisa's asking a second question, where we received 2 separate EPO plates from spaced SDSS. Quasar is nice to target using exotic. Is it possible to generate based upon? I do not know the answer to that, Lisa. I will have to think about that. If you can post this on our Slack channel, I can answer you on there. Maybe we can get back to you and think about that. Because I have never had to deal with photometric plates, luckily. I've been very spoiled and used live, digital data instead. All right. Barbara's asking, if Exotic is doing all the photometry and analyzing, then what is the purpose of AstroImage-J? Honestly, it's whatever your preference is. Some of our users like to use Exotic because that's what they started off with and that's what they're used to. Other people are experts on AIJ, and then that's what they're used to as well. And AIJ does a lot of the same things that Exotic does too, and it really is great. So for example, AIJ is more of a general astronomy program. It does the exoplanet transit analyses like Dennis Conti shows in his amazing workshop, but also it enables you to do, I think, variable star imaging, color photography, so astrophotography as well, whereas Exotic is just limited to transits. So AIJ has a lot more use cases than Exotic does. But honestly, it's whatever you prefer to do. If you like AIJ and that's what you use, then go for it. Still use AIJ. But if you'd rather use Exotic, then use it. That's the great thing about this amazing partnership we have, the AVSO. It doesn't matter what you use, as long as it's in the right format to upload to AVSO. And luckily, both Exotic and AIJ make that text file that you just upload to the database and hopefully get a published paper out of it. All right, I think that's all the Q&As. I don't know how we did that. That's amazing. Great timing, everyone. And I'm seeing tons of awesome chats in the chat. But honestly, if you do have any other questions or want to continue the conversation, again, the best way is to go and sign up on our Slack channel. That way you can continue talking with really helpful folks like Ira and Julio. You can see some really bad, terrible dad jokes from myself as well. And it's just a really great community of folks that can help you without everything from how to do your observations, how to do your analysis, whether that's AIJ or exotic, how to upload your data, how to get data from these robotic telescopes as well. So with that, I see you're at the top of the hour. Again, if you have any other questions, hop on our Slack channel. We'd love to chat with you. And thank you everyone for showing up. It's incredible how many people actually showed up for this webinar. I really appreciate 135 people. And Lauren, thank you again for asking me to give today's talk. I really appreciate it.
Absolutely. And thank you so much, Dr. Zellem, for a really excellent webinar. This has been so informative. Thank you.
Cool. And again, just go on our website to find our Slack channel link.
Yes, great advice. All
Cool.
right. So I'm going to go ahead and share my screen really quick. And we'll do a couple of quick closing announcements. So before we close out today's webinar, I would like to express our sincere gratitude to our 2024 series sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. As a reminder, registration is now open for next month's free webinar, which is scheduled for September 14th. This one will follow up on today's excellent presentation by Dr. Zellem by taking a deep dive into practical exoplanet photometry. You can learn more and find the registration link on our website at aavso.org/webinars. I hope to see you there. And our AAVSO annual meeting is coming up fast. It's scheduled for November 8th through 10th, and it will take place at the U.S. Space and Rocket Center in Huntsville, Alabama. Personally, I cannot wait for the event, and I hope that I will see many of you there in person in Huntsville. If you'd like to learn more about the program coming up for our annual meeting, or if you'd like to go ahead and register, you can find all the information that you'll need on our website at aavso.org/113. Now, to everyone who is out there in the audience, wherever you are in the world, I would just like to say thank you. Thank you for tuning into today's session and for making it such a wonderful, high engagement time. It is your participation in our webinar series and in all of our programs, which allows us to keep growing, keep educating, and keep making an impact on variable star science. So thank you. We really couldn't do it without you. Today's broadcast has been recorded, and if you would like to go back and reference the recording, you can find it on our Facebook page, where it will be automatically uploaded just as soon as the webinar ends in a minute. Pretty soon, we will also upload the recording to our YouTube channel, where it will join an enormous library of educational videos and recordings of past webinars, including, for example, Dennis Conti's past webinar on how to use AstroImage-J for exoplanet transit photometry. You can find Dennis's webinar along with the rest of our library on YouTube by searching for the username AAVSOHQ. When you leave the webinar today, you should be automatically shown a survey in your web browser. I would really appreciate it if you could take a minute and fill out the survey. Let us know what you thought of today's session and what we might be able to do differently or better next time. Now, to close, I would like to express a final sincere thank you to Dr. Rob Zellem from all of us here at the AAVSO. This has been an outstanding session, and we really appreciate your time, knowledge, and enthusiasm. Thank you.
Thank you, Lauren, for the invite. Really appreciate it. And huge thank you to the AVSO. You all are such an amazing group of folks and an amazing community. We could not do this without you at all. The Exoplanet database is amazing, and we actually really, really appreciate everything. So thank you, everyone at the AVSO.
That's wonderful to hear. Okay, thanks everyone for tuning in, and see you all next month.